is by Gill Fountain on hybrid bonding technology, enabling high-performance compute applications. Gill is a native of North Carolina and graduated from NC State University with a Bachelor of Science in Engineering, Electrical Engineering in 1980 and a Master of Science in Electrical Engineering in 1982. Following graduation, he worked in the Center for Semiconductor Research at Research Triangle Institute, focusing on device fabrication, low temperature plasma-based processing, and bonding technologies. In 2000, he joined Ziptronics as a founder focused on the development of 3D fabrication technologies using direct oxide-oxide bonding and hybrid bonding. In 2015, Xperi acquired Ziptronics. Gill works with the Xperi team to further development of direct bond interconnect to 3D integration, concentrating on the areas of CMP and DBI bonding layer fabrication. Gill has over 60 publications and 29 patents. Gill, you're on.
Okay, thanks very much, Larry. As Larry pointed out, today I'm going to talk about hybrid bonding technology, enabling high-performance compute applications. And I'd like to thank the other members of my team shown here on the slide who are involved in this work. First of all, I'd like to give a little review of 2.5D and 3D packaging market trends and some of the technology challenges. And then I'd like to talk about direct bond interconnect, our brand of hybrid bonding and its improvement over microbump interconnect. Then I'd like to share a little bit of my personal insights of the hybrid bonding evolution and how that's gone from the R&D stage to high volume manufacturing stage over the last few years. Then next after that, I'd like to present the test vehicle demonstrations that we have that we're working on at Xperi for face-to-face bonding, face-to-back bonding, and including 5-die stacks with DBI to DBI bonding, and also DBI to TSV bonding, and then fine pitch DBI to DBI bonding as well. From that, we have data including stack reliability, fine pitch connection yield, and with alignment analysis. And then finally, my summary. There was a really good article last year in Spectrum magazine about Moore's law, and maybe it's no longer the right metric for looking at the technology because the law basically looks at shrinkage of transistors and technology nodes, and the performance picture that this shows is somewhat misleading, especially since the technology node has shrunk a lot faster than transistor pitch, and not really a good overall system performance. And it also obscures the fact that alternative methods to the node shrinkage are being developed and used to drive computing performance forward. Some of these methods are new materials for transistors to improve transistor performance, innovations in computing approaches, and the one I'd like to talk about, innovation in packaging and chip architecture, including 2.5D, which has been going on now for some time, 3D plus interposer, which is happening today, and also the addition of high interconnect density with hybrid bonding, which can further the enhanced performance. This is one method of metric that was presented in the paper called the LMC method, which looks at 3 different factors to evaluate performance: density of the logic, density of the main memory, and density of interconnects linking these. And I like this picture because it really gives an idea of, in the interconnect, the advantages of going to 2.5D and 3D over just simple flip chip, where the 2.5D, even with micro bumps, gives about a 10x increase in interconnect density, while the 3D plus interposer gives about 100x increase in density. And we would expect even further increases in density if we use hybrid bonding with the DBI technology. If we look at monolithic versus chiplet on substrate comparisons, the monolithic designs really could have potentially the highest performance, but they also have the highest design cost and risk, longest time to market, and basically inefficient use of resources due to mixed functions that do not scale. If we go to the chiplet on substrate, we can get good performance, reduced design costs, reduced design risk, and reduced time to market. One of the big advantages is using the most optimum process node for the function needed in each chiplet. And there's an example here from AMD of their chiplet design with a 14 nanometer IO die and 7 nanometer CPU chiplets surrounding it. This gives a little more detail on that part, where we can see that the chiplet architecture reduces the cost over the monolithic architecture by about a factor of 2 in almost every case, every performance case. And it also shows that an even higher performance was attained with the chiplet design than could potentially be attained with monolithic. And you can see also that if it's desired, you can scale down the cost with performance by just putting fewer chiplets on the part. And the part, again, uses this legacy node for the IO chip, which reduces cost. And then the CPU chiplets use a 7 nanometer node to optimize yield and performance. So flexible architecture of mixed nodes, smaller die, and distributed functionality delivers improved performance with lower fixed cost. This slide shows our branded DBI Ultra process for die-to-wafer bonding. And this basically uses very standard processing technologies that foundries have in place currently. Standard copper damascene, clean and dice, and it also uses die handling on tape, which is very advantageous for working with different die sizes down to very small sizes. And it allows flip chip pick and place of the die on the wafer, followed by batch annealing. So it's simplified processing with higher interconnect density than microbump. And this slide shows something we're pretty all familiar with, the hybrid bonding process, where we have first an oxide to oxide bond with recess of the metal. And then after heating, the metal expands and pushes in from each side, giving a thermocompression bond with no need for applying external force. And the good thing about this is, as we've been hearing this morning, it's scalable to 1 micron or below for pad size. It can be achieved over a temperature range. We've demonstrated the temperature range of 150 up to 400 degrees, depending on the design of the parts, the design of the DBI structures. And then it's compatible with a number of different dielectrics, silicon dioxide, silicon oxynitrides, and SiCan as well. In looking at the advantages of the hybrid bonding over microbumps, one of the big advantages is that there's no underfill needed for the technology. So this helps tremendously with the thermal issues. And also there's improved electrical performance from the copper to copper bonding. The microbumps have more of a cumbersome process with lithography and solder plating, whereas the DBI copper to copper bonding reduces process steps and math steps and provides a pathway to reduce cost. And one of the biggest advantages is that the pitch that can be achieved can allow up to over 1 million connections per millimeter square, whereas microbumps are going to be limited in that range. This was some modeling that was done to show the enhanced electrical performance. And as we saw from the last talk, there's basically reduction of capacitance for faster performance, less resistance for lower DC power drop and less heating. And there's less self-inductance as well for less signal distortion. And again, with the thermal performance, we found that the stack with the DBI hybrid bonding acts more like a single die than the microbump stack. Okay, so now one thing I'd like to talk about is some of how hybrid bonding came into development at Ziptronics back in the 2003, 2004 timeframe. And a lot of this came from challenges that we had in our prototype fab, where we had limited resources to build parts. We were trying to build SoC type parts, where you can see an example here where we had flash memory combined with the CPU and FPGA on a 3x3 array of DRAM. And at this time, we didn't have any, there was no type of hybrid bonding technology, and we were making over the edge connections to these parts, which was a very difficult process given our limitations in the fab. First of all, the thinning these die for face-to-back bonding was a very cumbersome process involving a direct bond to a carrier wafer and then back grinding and thinning, and the die had to be made 20 microns thick and then bonded and the carrier material removed. So there was a lot of work in that, and face-to-face bonding would have been much better. We had trouble with making a planar aluminum RDL in this point, and because we didn't have any tungsten plug technology. So what we did to try to remedy that is we came up with a nickel plug process using CMP. And what we found was that when we polished that, made a very flat bondable surface. And so that's really how nickel DBI was born. The first hybrid bonding that we did with nickel pads. And later, we, with CMP development of copper, we were able to develop copper DBI as well. And again, the over-the-edge connections with organic planarizing materials was very difficult, and this was much easier with face-to-face bonding with DBI hybrid bonding. This slide shows kind of a timeline of how all this happened, starting in 1998, where we were working on plasma-enhanced direct bonding of 3,5 materials to aluminum nitride for millimeter wave circuit building. And this technology led to the spin out of Ziptronics in the year 2000, where we started developing die-to-wafer direct bonding for integration. And then in the 2004-2005 timeframe, we came up with the first nickel-to-nickel DBI parts. And we soon started doing prototype demos for people, including some world-class foundries that we did demonstrations for at that time. Later, we extended that to wafer-to-wafer bonding. And then in the 2009-2010 timeframe, the copper to copper DBI bonding with demonstrated pitches as low as 2 microns. In 2015, we were acquired by Xperi, and we started looking at more of a high volume manufacturing process for die to wafer, solving some of the fundamental challenges of reliability, stacking, fine pitch, and lower total thermal budgets for the bonding. And on the manufacturing timeline, in about 2009, Raytheon became our first licensee of DBI bonding. Later, Sony licensed our direct plasma activated bonding process for their backside illuminated camera chips. Then in 2015, Sony licensed the DBI technology for their more advanced camera chips. And since then, a number of foundries have licensed the technology from Xperi, including UMC, Samsung, SK Hynix, Tower Semi, Canon, and most recently, YMTC. So now I'd like to just go into the test vehicles that we have. We have 2 different flavors of test vehicles. One to look at memory issues, including stack structures, processing temperatures of 200 C or lower to preserve the memory performance. Large pads that have been polished to meet the topography specification and the alignment, also the alignment tolerance of available pick and place tools. And for this, these parts, we've focused on this presentation on reliability data that we've gotten. In the logic flavor, looking at supporting disaggregation, disaggregated chiplet architecture. We're looking at fine pitches with smaller pads. And in this case, especially for die to wafer pick and place, high accuracy alignment tools are not routinely available, but they're being worked on currently by the equipment manufacturers. The high accuracy wafer to wafer tools have been available for some time, but not necessarily high speed, high alignment die to wafer. And with this logic part, we're looking at connection yield and alignment for fine pitch. And just one note that our prep lab is here in North Carolina and our bonding lab is in California. So we've demonstrated that we can prepare wafers for bonding and ship them to another location for the bonding activity, and with very good results. And this is just shows how parts could be, for example, built and prepped for bonding at a foundry and shipped to an OSAT for assembly. So this shows our 2 test vehicles for memory. These both have pitches on the order of 35 to 40 microns. The one on the left is a single layer structure, which has a 40 micron pitch and a chain, main chain in the center with about 31,000 links, and smaller chains around the periphery of the die. These chains come within a couple of hundred microns of the edge of the die. So we can evaluate some edge effects from that. With the die on the right, this is our stack structure. And in this case, most of our data is from 5 die stacks, although the structure could actually build as many layers as you wanted to theoretically. It has basically a bottom host wafer, and then TSV wafers, TSV die, which are 50 microns thick with 5 micron diameter TSVs. And those are stacked. On one side, they have DBI connected to the TSV, and on the other side, just the TSV, so that the first bond is DBI to DBI. The subsequent bonds are face to back, TSV to DBI, and then the last bond is TSV to DBI in what we call the cap wafer. which completes the daisy chain. And in this case, we have 4 different chains. One in the center has about 9,000 connections. One on the left and the right have about 600 connections on each. And then there's an edge chain that's about 80 microns from the edge, again, for evaluating edge effects. And it has about 2,500 connections in that particular chain. This shows our reliability testing and results. We've done basically temperature cycling, high temperature storage, autoclave, HAST type test, and moisture sensitivity test. And both the single layer parts and the 5-die stack parts have passed all of the tests that we put these through. And basically, the hybrid bonding interconnect should be more reliable than the micro bump. First of all, because there's no underfill, and it's an all copper interconnect, so there's no void formation from solder and intermetal formations, no cracking of underfill, that sort of thing. It has enhanced resistance to electromigration because it's an all copper interconnect. And it also has good hermeticity from the dielectric bond, which has about less than 10 to the 11 atmosphere cc's per second leak rate. This is a cross section of our 5-layer stack with TSVs and TSV to DBI bonding. And on the left, we have the time 0 picture of the stack, and then on the right, after 2,000 hours, you can see there's no degradation in the parts, no void formation, and basically with copper to copper joints, there's no driving force for void growth. This next slide shows our fine pitch test vehicle, which again, it's an 8 by 12 millimeter part. In this case, the die are 200 microns thick. We have a 2 micron pad on a 4 micron pitch and 5 different daisy chain arrays. The main chain array has 1,600,000 connections in the center of the die. And then we have surrounding daisy chains around that with fewer connections. One with interleaved connections, so we can check both continuity and leakage between the chains. This slide shows the Asana Scan, typical Asana Scan of one of our data wafer bonds with this part. And basically, we've been able to achieve in our facility in California over 95% void-free die. And this is similar to the work we've done a lot more work with quartz pitch material, but it's very similar results. And probably the voids that we're seeing are caused by the manual handling of wafers and die frames that we have to do for loading into the bonder. And we would expect higher yield than this with automated handling in an HVM facility. This shows a cross section of the 4 micron pitch parts, daisy chain. And we can see that the dielectric to dielectric interface shows no gaps, which might be caused by rounding of the oxide during CMP. It indicates a good CMP process and clean surfaces. The copper to copper pads are kept completely connected with no gaps or voids, indicating we've had sufficient anneal and temperature and time to close that and make that connection. You can see a close-up of the copper to copper interconnect here. With the 250C anneal, we're getting better than 80% electrical yield on these large chains. Some of the yield loss is attributed to a foundry fabrication issue we had because we had actually requested a sort of a non-standard process from the foundry with a single damascene DBI process, where they normally do a dual damascene process. And so we're fabricating a new test vehicle now, which we expect to get higher results in the electrical yield. This shows a very interesting effect that we've noted on the alignment or misalignment of the chains and how much misalignment we can tolerate. So on both the coarse pitch and the fine pitch, we're seeing that an 80% misalignment of the pad size can be tolerated before we start to see a drop off in the connection. So this is data from a single wafer showing, or multiple wafers showing that with these various alignments, which are sort of the results of the pick and place and the variation of the pick and place, everything is connected with the 10 micron pad up to 8 microns of misalignment, and then it just drops off. And with the 2 micron diameter pad, everything seems to be connected up to about 1.6 microns, and then it drops off. So it's interesting that with these two pad sizes, we're seeing roughly the same tolerance percentage-wise for misalignment. This data here shows the effect of misalignment on our chain resistance. So this is the resistance of the entire chain, and we're only seeing about a 9% change in the case of the fine pitch with the 80% misalignment, and with the coarse pitch, we're only seeing about a 6% increase with this 80% misalignment. So the misalignment of the DBI copper to copper interconnect is causing a relatively small change in the overall chain resistance. Of course, the exact value of this would depend on the details of the DBI and RDL designs. So, in conclusion, with transistor size limits and lithography limits being approached and monolithic SoC costs rising, the industry is focusing on 2.5D and 3D integration solutions for increased system performance and lower cost. DBI hybrid bonding brings significant value to 2.5D and 3D with cost reduction, performance enhancements, and technology scaling. Hybrid bonded test vehicles with single and 5-die stacks have been built with 35 micron HBM-like pitch and 4 micron logic-like pitch, all with high electrical yield. The DBI interconnects have shown superior reliability performance. And basically, the industry should be well positioned to manufacture 2.5D and 3D packaging with this type of DBI hybrid bonding technology. Just a final slide here. Direct bond interconnect where less is more. This DBI Ultra process offers for DBI TSV stacks, minimal processing after TSV planarization for high bandwidth memory, no standoff, no underbump metallization, no underfill, no heat needed during the bonding, and just a low anneal temperature after all the copper to copper to anneal the copper to copper bonding. More cost savings, higher throughput bonding, improved thermal performance, higher speed bending stacks, and improved reliability and yield. And then also, as we saw earlier today, possibility of heterogeneous integration. With DBI to DBI face-to-face stacks, less pitch constraints, again, no standoff, no underbump metal, and no underfill. More scalability, more flexibility in architecture, proliferation of chiplet concepts, and uniformity across packaging platforms. So all this enabling advanced memory and high performance compute roadmaps. So thank you, and we'd like to thank our partners at Fraunhofer for the 300 millimeter silicon wafers with TSVs, Tower Semi for the fine pitch DBI silicon wafers, and L Foundry for the 200 millimeter coarse pitch DBI silicon wafers. Thank you very much.
Thank you, Gil. There are a couple questions in the chat from Randy on the alignment slide. Curious that the data looks bimodal and the pitch data manifesting skew. You have any thoughts on that?
So I'm not quite sure I understand the question. It looks, can you repeat the question?
Randy, do you want to comment on, clarify? If you want to unmute yourself. I'll repeat the question. The data looks bimodal on the alignment, and the pitch data shows some skew.
Well, we did see some effects on the alignment that looked like they were due to our bonding tool. We saw like a some localized misalignment on from that were the same from wafer to wafer on our bonding tool, and on our partner's bonding tool, they didn't see that same misalignment. So there could be some tool related alignment issues in this data. I guess the main point of the data was this fact that the electrical connection was good out to 80% pad size offset.
Okay, and there's a question from Johan Mechtel. Can you comment on yield issues, if any, attributed to the shipping to your California facility and finishing the process only there?
Yeah, so you certainly have to be careful in shipping parts from one place to another, and we've tried to use various techniques to we vacuum pack the parts, and in a lot of cases we'll include desiccant in the packaging to keep things dry. The parts definitely can go through temperature cycling and humidity changes in shipping. In general, it's not thought of as a good thing to ship copper parts with exposed metal around the world. And there are ways to protect the surfaces, temporary protection of the surfaces that can be done as well. And this is part of what Xperi teaches in their technology transfer, is how to manage these types of things. Because if you have copper oxidation, that's certainly gonna can cause a problem, especially if it's severe. It can cause the parts to be ruined for bonding. So there are issues like that. Also, you have to be sure that your shipping containers don't create particles and things like that as well. So there are a number of aspects of that to be considered. But we generally, the wafers go through thorough cleaning once they arrive at the spot for bonding. And so that's another part of in making sure you preserve the yield, is to make sure you have a proper cleaning technology before bonding.
Thank you.
Any questions in the room? Actually, I have a question.
Yeah.
Maybe I'll come to I have a question. In the keep on stacking experiments you've done, what are the trade-offs? How thin can you get the wafers and be able to keep stacking?
So that's a good question. At 50 microns, the wafers are already getting pretty fragile, the die. And so a lot of that depends on the pick and place tool, having it set up so that you don't crack the die when you peel them off the tape and that sort of thing. I know die are being stacked currently, I think for HBM with thinner than that. So it is possible to handle the parts, but a big part of it too is managing the processing of the wafer so you don't create weakness in the silicon during the processing. If temperatures are too high or that sort of thing, we've seen creation of weakness in the silicon itself, which can cause cracking, potentially from the expansion of the TSVs and that sort of thing during the processing.
Couldn't you bond face down and then thin? And see the thinner wafer that way?
Well, it would be possible.
Can you repeat the question, please?
Yeah, so Paul asked if we could bond face down and then thin the die right afterwards. And that is possible, but the processing is a lot more difficult. Once you have a die bonded on a surface and you have these gaps in between, it's very difficult to do good CMP because the edges get very rounded and that sort of thing. So we've tried to come up with processes that are much more able to just have a part that's ready to bond on both sides. So there's no processing after the bonding other than maybe cleaning.
Thank you.
Okay.
Any other questions?